So thermochemistry is the study of the relationships between chemistry and energy, prefix thermo referring to energy. So we need some definitions. Energy is the capacity to do work. It doesn't mean that work is being done, but there's the capacity to do work. And we have to define work. A scientific definition is that work is a force acting over a distance. So if I take this wash bottle and I push it and slide it across the bench, that's work in the physics definition. I've applied a force through a distance. Heat is the flow of energy that's caused by a difference in temperature. A lot of these things get kind of all muddled in our brains. Heat, energy, temperature, these things are a little hard to distinguish. So heat is the flow of energy. Energy can flow because of a temperature difference. And we are familiar with this. If you hold a hot cup of coffee, your hand gets warm, right? There's energy being transferred from the coffee to your hand. The reason we put ice cubes in a drink is because the ice cubes absorb energy from the drink and cause it to become colder. Energy flows from a higher temperature to a lower temperature. So it's helpful to think of energy as a quantity that an object or a group of objects can possess. It's something you can have. I like to think of energy as being a lot like money. You can have money, you can spend money, you can receive money, right? So energy is like money. Here in this picture we have a billiard ball and it's rolling across the table. It is in motion, it has energy because it's in motion. Heat and work are ways that objects can exchange energy with other objects. So when this ball collides with, the white ball collides with the purple ball, what happens? Well, the white ball had more energy than the purple ball, is going to transfer some of its energy or possibly all of its energy to the purple ball. The white ball hits the purple ball starts moving. Energy has been transferred. That type of energy is work. So the white ball did work on the purple ball and transferred energy. So energy can move into an object or out of it, just like money can go into your wallet or out of it. Any questions yet? There are many different types of energy, and it really comes down to two broad categories: kinetic energy and thermal energy. Kinetic energy is the energy of motion. Thermal energy is associated with, back that up. Kinetic energy and potential energy, two main categories. Kinetic energy is still the energy of motion. The other category, potential energy, is associated with, we typically think of the position of an object, but it could also be the composition of an object. So if we have a ball raised above a surface or a Sharpie raised above the floor, this has potential energy. Because if I let go of it, what's going to happen? It's going to fall. It's going to start moving. It doesn't have much kinetic energy right now because I'm not like waving it around, I'm holding it still. But as soon as I let go, it's going to start moving. So it has the potential, right? Yep, goes to the floor every time. So the other types of energy can be put into categories of kinetic or potential. So thermal energy is the energy associated with temperature. So something that has a higher temperature has more thermal energy. Something with a low temperature has less thermal energy. Thermal energy is actually a form of kinetic energy. I've talked to you before about the 3 states of students correlating to the 3 states of matter, solid, liquid, and gas, and pointed out that even when you're stationary in lecture, which is the solid state of students, you're not moving around, everyone is still moving, right? Some of you are not moving very much. It's only 8:15 in the morning. I completely understand that. But everyone's breathing, right? Some of you are taking notes. You might be fidgeting, looking around. You're moving. That's kinetic energy, right? So thermal energy is a form of kinetic energy. It just doesn't necessarily involve traveling from one place to another. You can have a lot of kinetic energy without going anywhere. We could all get really agitated and just be jiggly wiggly in our chairs, right? That would be equivalent of a higher temperature solid. Anybody have any questions about that? So thermal energy is a form of kinetic energy. Another type of energy important in chemistry is chemical energy. And this is a type of potential energy. So it's not associated with me holding a marker above the ground or a piano hanging out a second floor window, right? Those have potential energy. They're unstable. It has to do with the relative positions of the particles inside of atoms and molecules. So the relative positions of protons and electrons. We can think of some compounds as being like compressed springs. They contain potential energy which can be released in a chemical reaction. You press down on a spring, and as soon as you let go, it's going to expand, and if there's something on top of the spring, it'll shoot it up into the air. Any questions? So this is a flowchart summary. Energy is the capacity to do work. We've got kinetic energy due to motion. Thermal energy is the motion of the individual particles, not necessarily relative to each other, but just wiggling around. It's associated with temperature. Potential energy due to position or composition. Chemical energy is a type of that, associated with the positions of electrons and nuclei. So the law of conservation of energy, which was mentioned in the quote at the beginning of the chapter, states that energy can be neither created nor destroyed. We can transfer energy from one form to another. Energy can take on different forms. We can transfer it from one object to another, but you cannot create or destroy energy. So here we have an example, much like the pen that I was holding earlier, but the YouTube viewers can see this one. You hold this ball above the surface of the pool table. It has gravitational potential energy. Potential energy due to its position elevated above a surface. We drop the ball, and that potential energy decreases as it gets closer and closer to the surface, but the kinetic energy increases because it goes faster and faster as it falls. So potential energy is turned into kinetic energy. Here's an example of a spring. So the woman is pushing down on the spring. There's a ball on top of the spring, and you push down. You're putting energy into the spring. This is mechanical potential energy. When she releases the ball, the spring expands and shoots the ball up into the air. The mechanical potential energy has been transformed into kinetic energy of the ball moving. So when we look at the exchange of energy, we have to be very careful in how we define what's losing and what's gaining the energy. So we talk about the system and the surroundings. So the system is what we're looking at. The material or process being studied. So if we're looking at the hand warmer, we're looking at the system as being the iron that's inside the hand warmer. The surroundings, everything with which the system can exchange energy. So there the system would be your hand, your glove, the air inside the glove, even the air outside the glove, anything that can receive or contribute energy to the system. The definition of system and surroundings is up to the person looking at the problem. And it can be very important to define these things in the correct way. So conservation of energy means that energy, the amount of energy that's gained or lost by the system has to be equal to the amount of energy lost or gained by the surroundings. So here we're representing our system as having an energy gauge, kind of like a gas gauge. I came into work this morning and I made it, but it's running on empty. So here this system energy gauge is half full, and the surroundings energy gauge is a quarter full. When an energy transfer occurs, the amount of energy that's lost by the system has to be gained by the surroundings. So here the system has lost a quarter tank, the surroundings have gained a quarter tank. There's no making energy or destroying energy in the process. It's a lot like money. So when you buy and sell things, the total amount of money remains the same. That what's different is who has the money, right? If I pay you $5 for something, if you're selling giant candy bars for a fundraiser, I give you $5. Okay, I'm out $5, you've gained $5, but the $5 is still there, right? It's just moved. Total amount of energy is constant. So if we have a quantity like this, of course, we want to be able to measure it, and to measure something we need units. There's a variety of units used for energy. An object of mass m moving at velocity v has a kinetic energy ke given by this equation. Kinetic energy is 1/2 the mass times the velocity squared. So that's good for something traveling through a distance. This is where you get, the train is going so many miles an hour and it weighs so much, and you can calculate the kinetic energy of the train. Trains have tremendous amounts of kinetic energy. Stay clear of them. Every year, somebody dies on the train tracks out here. Don't mess around with trains. Little public service announcement there. If we use the units kilograms and meters per second, those are the SI base units for mass and speed. We get the SI unit of energy, which is the joule. It's got a weird spelling, Joule, but it's pronounced joule, just like a gem, jewel, Jewel. A joule is 1 kilogram meter squared per second squared. This is a relatively small unit. So if you think of a 10-watt light bulb, that's a pretty low wattage light bulb. That would use 36,000 joules in 1 hour. Just kind of for reference. We can apply metric prefixes to these units as well. So a kilojoule is 1,000 joules, just like a kilometer is 1,000 meters. Another unit of energy, which you might be more familiar with, is the calorie. This was originally defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And there's a relationship between calories and joules. And this is a defined relationship now, so this is exact. 1 calorie is 4.184 joules. This calorie is not the calorie you hear about in commercials or see on the nutritional information on the food that you eat. That's the nutritional calorie. That has a capital C. abbreviation is capital CAL. This is a lowercase c. Like, that's not confusing, right? This is nutritional calorie is actually a kilocalorie. So a kilocalorie is 1,000 calories. A nutritional calorie with the capital C is a kilocalorie. I don't generally set out to trick you on an exam, but it's happened in the past. If you see a capital C on an exam with calorie, it's not a typo. That's a capital C, it's a nutritional calorie. A lowercase c is a regular scientific calorie. Another energy unit, which is larger, is the kilowatt hour. And that's what PG&E uses for measuring electricity on your bill. That's a unit of energy. It won't come into our problems very much in chemistry. So here are some relationships. The calorie is 4.184 joules. The abbreviation is a capital J. The nutritional calorie, or a kilocalorie, is 1,000 regular calories. And so then it's 1,000 times 4.184, or 4,184 joules. And a kilowatt hour is this many joules. Table 7.2 just gives us, in the different units, the amounts of energy needed for these different things. Raise the temperature of 1 gram of water, 10-watt light bulb for an hour, amount used by the human body in running 1 mile. So in nutritional calories, that's 100 calories. It sounds a little better in scientific calories because then it's 10,000 calories, right? That sounds like you're doing more. Or 4.2 times 10 to the 5th joules. This is just for your information.